Hey, chemistry, how are you? I really, truly hope and pray that you're all doing well. And those of you who don't feel like you're doing well, reach out to me or to another teacher that you trust. Let us know how it's going. But chapter 13 is gas laws. If you haven't noticed with the assignment that was due last week, it's just hit the tip of the iceberg with this chapter. We have skipped chapter 12. Chapter 12 is ideas like melting and freezing and things that you probably already learned in middle school, and they're not on the standards for chemistry. So we're skipping to chapter 13, which I think is a more important topic about gas laws. Here in front of you, you see three gas laws: Boyle's laws, Charles' laws, and Gay-Lussac's laws. And these three laws state how pressure, temperature, and volume are all related. So these are famous chemists or physicists who figured out how pressure, temperature, and volume are related. And it turns out that they're pretty simple equations. Notice there's not a whole lot here besides P's, T's, and V's. So that's pretty awesome. It looks like a lot to handle, but I'm about to show you an equation that kind of combines all of these ideas into one. So it's not necessarily important that you memorize all these. Maybe if we were having class, we would work on some of that, but I think I'm gonna just ask you to know the overall equation, which I'll show you in a minute. But let's talk through these real quick. Boyle's law shows that pressure and volume are inversely related. Now, as it's written, it doesn't look inverse, does it? It kind of looks like just multiplication straight on through. But if you think about what happens with the math here, let's consider some simple numbers like 5 times 2. Let's say the pressure is 5, the volume's 2, that's 10. But if the pressure's 10 and you solve that, if 5 times 2 has to equal 10 times something, and that something is going to be 1, right? 5 times 2 equals 10 times 1. That's 10 equals 10. And what just happened there is we did 5 times 2 equals 10. The pressure went up, but 10 times 1, when volume was originally 2, the volume went down. And so mathematically, even though it looks like just a bunch of multiplication happening here, pressure and volume end up being inversely related. If one goes up, the other one goes down in value mathematically. Charles' law, as you look at it in pink here, is a direct proportion, actually, even though there's some division involved. Because if volume goes up, then temperature has to go up as well, because this is a fraction. So if this was 5 over 5, that's equal to 1, that could equal like 7 over 7. That's also equal to 1. So those are some values that you could fill in here to make this equation true. 5 over 5 equals 7 over 7. That's true because those both equal 1. So as 5 changed to a 7, volume went up. As a 5 changed to a 7, temperature went up. So these two are directly related, whereas if volume goes up, temperature also goes up. And so Charles' law shows that those two are directly related. Gay-Lussac's law is another direct relationship, this time between pressure and temperature. And for all the same mathematical reasons, when pressure goes up, temperature goes up. And that kind of makes sense, right? If you think about it, if you have something that's super pressurized, it's probably at a high temperature as well. So just kind of with everyday life things, you might always think of like higher pressure means higher temperature. So those are directly related, even though they involve some fractions. And so, as you may notice, we have a combined gas law that really combines all three of these laws all put together. Notice that your P is always in the numerator. Notice that your V is always in a numerator. And notice that your temperature T is always in a denominator. And so all three of these kind of work hand in hand to show how pressure, volume, and temperature are all interrelated and all affect each other. I'm going to put up some Edpuzzle videos to kind of drive this point home in a more visual kind of manner, so that you can understand the ideas behind the ideal gas law. However, I thought I would take this video that I'm teaching you and give you some more of the math hints behind what you'll need to do with the math in this section. So consider this first problem. So if you're really good at math and you passed Algebra 2 with an A, you might be able to pause the video now and actually try this problem out the first time you see this video. But for those of you who struggle a little bit more in math class, you're going to want to watch this video twice through and really push pause and try these problems out. So let me give you an opportunity right now to push pause and try it out. You may notice in this problem that we're dealing with volume and temperature. They don't mention pressure in this problem, which implies that the pressure is constant. So if you take a look at this combined gas law and just simply cross off pressure, you're going to notice that volume and temperature are left, which is Charles' law. So basically, we're going to be using Charles' law in this problem. And you can even just take the combined gas law, cross off pressure, and derive Charles' law from the combined gas law, which is why you don't necessarily have to memorize all these, because if you know this one, then it's like you know them all. So let's write out what we have from the combined gas law once we take away pressure. V1 over T1 equals V2 over T2. So one of the first things you're going to want to do in these kinds of problems is figure out where your missing variable is. We have a volume and a temperature and another volume, and it says at what temperature. So this one right here is the variable that we need to solve for, this T sub 2. We're given initial conditions, which you can think of as sub 1, but your sub 2 are like the new conditions that you're trying to figure out. Some of you with the algebra here might struggle a little bit, but once you practice these a couple times, it'll come back, those algebra skills with the equal signs. So for solving for T2, we can use cross multiplication here to get rid of fractions. So if I cross multiply this, this is V1 times T2 equals T1 times V2. And remember, the T2 is what we're solving for. So to get the T2 by itself, we will divide the V1. Remember, these are being multiplied in a math class. To undo multiplication, we divide. So we will undo that, and therefore these cancel. And we have T2 solved for. So T2 T sub 2 equals T sub 1 V sub 2 over V sub 1. Voila, we've got our equation to work with. Excellent. As you plug these numbers in, you have to be careful because temperature here is given in Celsius, and in this chapter a lot, it's really important to be in Kelvin. So Celsius is 12 degrees, but we need to say plus 273 to convert to Kelvin. And our V2, we were given in the problem 6.0 kiloliters, and our initial volume was 5.3 kiloliters. So you'll notice here as we're working within our units that the kiloliters cancel out. So our final answer should be in Kelvin. And if you throw all that in your calculator, hopefully you got 323 Kelvin. Now, what you might need to do to match the answer in the solutions guide, or if they ask you to in the problem, is to convert back to Celsius. And to convert back to Celsius, we subtract 273, and that converts you to 50 degrees Celsius. As a general rule of thumb in chemistry and in physics, if they start you out with Celsius, you should probably end in Celsius, even though you need to convert to Kelvin in order to work out this problem. So let me pause there and come up with, I think we probably need one more practice problem. And so let's read this next problem together. It says a sample of nitrogen monoxide has a volume, a temperature, and a pressure. So it looks like we're dealing with volume, temperature, and pressure in this problem. So all three variables, there's not going to be one that we cancel out this time. It says what volume will the sample occupy at a different temperature and a different pressure? So if it says what volume, then basically we know we're looking for V2. So I recommend that you start off these problems by writing down your combined gas law, and then solving for the variable you know you need to find, because it's a lot less messy that way. And this is also the standard in physics, that you find the variable first and then you plug in your numbers. So it says, at what volume will the sample occupy a certain temperature and pressure? That means we're trying to solve for V2. Now remember in your algebra days that you were taught an easy method to solve for a variable that is being multiplied and divided. So let me show you that now with a different color. We're trying to get V2 by itself. But in order to get V2 by itself, we need to move over the P and move over the T. So your T2 is being divided. We undo division with multiplication. And the P2 is up in the numerator. It's being multiplied. So we undo multiplication with division. And of course, as in all algebra classes, what you do to one side, you have to do to the other side to be fair. So if you're multiplying by a T2 over P2, you better also do that on the other side. And voila, we have our variables canceling. And we have our V2 solved for. So V2 is now by itself. And on the other side, we have a whole bunch of other things. So let's bring it all together. T2, P1, V1, all over P2, T1. So everything's lined up, ready to substitute into that equation to find our final answer, V2. So go ahead and substitute those numbers, divide out these numbers, and see if your final answer matches mine. Push pause. So here are all my numbers substituted in. Hopefully you did a really good job converting to Kelvin before you attempted to plug in temperature into this problem. Kelvin and Kelvin cancel out. Kilopascals and kilopascals cancel out. And you'll see milliliters is the unit we have left. Plug all these numbers into your calculator. 297 times 104.1 times 72.6 divided by 99.3 divided by 289. Very careful with the way you plug this into your calculator. Do not skip this step during this lecture to actually try it out yourself, plugging it into your calculator, because if you have any calculator trouble, you need to fix that now before you get to a quiz or test. So as I plug that all into my calculator, you should get 78.2 milliliters for your final volume. Don't ever forget sig figs. Don't forget units. We need to know what we're measuring things in. Is it milliliters? Is it liters? Is it gallons? Is it something else? So make sure you're including all of that, being really good to show units all the way through and canceling. This is going to be an excellent skill too when you hit physics next year. So do practice all of this now. It is required on your homework, remember, to show all your units and all your work. And a lot of you have been really great at that all the way through this school year. So I'm going to call that good for now. That's a lot of the math you're going to see in this chapter: rearranging variables, being good with your units, and working with this equation of the combined gas law. Good luck, you guys. Get that homework done. Watch those ed puzzles to really understand the pressure, temperature, volume relationship. And let me know during office hours if you have questions. Bye.